Hi, I'm Zach with HKN, and today we're going to do a problem involving complex power and a load impedance that has also a complex value. So we have two problems to do with this circuit. First, we have to find the value of the load impedance for maximum power transfer. And second, we have to find the average power delivered to the load for our source voltage being 80 times cosine of 5,000 t. So, for the first part, we need to find load impedance for maximum power transfer. And in this, the same principle holds that held for purely resistive circuits, where if your resistor is equal to, if your load resistor is equal to the Thevenin resistance of the circuit around it, then you'll get maximum power transfer. So we'll just solve for the Thevenin impedance around this, and when your load impedance is equal to that, we'll get maximum power transfer. So these two elements have some value of impedance. It's going to be complex, and it's going to depend on the value of frequency that the circuit's running at. So, and that's determined by the source. Whatever frequency the source is running at is the frequency the whole circuit's running at. So we see that the source is running at 5,000 radians per second. And so we'll assign values Z1 and Z2 to the inductor and capacitor. Now Z1, the impedance for an inductor, is equal to J times inductance times frequency, angular frequency. That's equal to this, we already did out the math, and that is equal to J40 for this particular value of oscillation. Now, the impedance of a capacitor is equal to 1 over J times capacitance times frequency of oscillation. And when you do the math out for this, at this frequency, this capacitor has an impedance of minus J40 ohms. So now we have a value of impedance for every element in the circuit, because the impedance of the resistor is just the resistance. So we're going to find Z Thevenin around this using those values. Now, we can do the kind of shortcut way. We can short our voltage source and find the equivalent resistance between these 2 points with the voltage source shorted. So what that's going to do is it's going to put this in parallel with this, and then we're going to add this to it. Because with this shorted, these have common nodes, and then this is just on top of those, basically. So what that is going to give us is that your Thevenin impedance is equal to this impedance in parallel with this impedance, that is 40 ohms in parallel with J 40 ohms. And that's the value for the set of these two in parallel, and then we're just going to add this resistance or impedance to it. So, and that impedance is minus J40. So that's the value of your Thevenin impedance. So this simplifies down to ohms over 1 plus J, and that, if we multiply the numerator and denominator by the complex conjugate of this, well, we don't like to have complex numbers in our denominator, so the way to get rid of that is to multiply both top and bottom by the conjugate of this, which is 1 minus J, and that results in 20 ohms times 1 minus J. So that's our value for our Thevenin impedance in between these 2 points. Without, we can kind of just imagine that the load impedance isn't there. We're just looking for the impedance between these 2 points without that there. So that's that value. Now okay, so it's not exactly like the resistive rule. For maximum power transfer, your load impedance has to be the conjugate of this number. So when we try to find the conjugate, we just take the opposite imaginary value. So for maximum power transfer, your load impedance has to equal 20 ohms times 1 plus J. So this is the value of load impedance that'll give you maximum power transfer. All right, now for the second part of our problem, we are going to find the maximum average power delivered to our load impedance that we solved for in the first problem. Now, the formula for maximum power is 1/4 times your Thevenin voltage, the RMS value of your Thevenin voltage. We'll talk briefly about what that is. It's basically the average effective voltage, and then this is divided by RL, which is the resistive part of our impedance. We have a resistive part and a reactive part, and RL is basically the real part of your load impedance number. So we have to solve for V Thevenin and find its RMS value. So we're going to take the load, we'll just erase that. We're going to erase this and solve for our Thevenin voltage in between here and there. Right away we can see one thing: no current can flow in this branch, so there's going to be no change there's never going to be a change in voltage across this capacitor. So the voltage here at this node, we'll call this node 1. The voltage here is always equal to the voltage here. That's because nothing can happen with this. It just floats at whatever value this node's at. So we'll write a KCL equation to find this voltage right here. We'll have a current here, a current here, and those should sum to 0. There's no current in this branch again. So we'll say that we could call this V1, but we're going to call it V Thevenin since we know that's what we're looking for, and that's going to be equal to V Thevenin. So we're going to have V Thevenin minus your source voltage all over the impedance of that inductor, which is J40. That's this current right here. And this current right here is going to be equal to V Thevenin over 40. That's how the resistance of that resistor right there. And these have to equal 0. Alright, so now we have our node equation, and we're going to rearrange this so that we can get V Thevenin in terms of our source voltage. So if we rearrange this, we'll keep V Thevenin on this side here. Now, the terms in this equation that V Thevenin is multiplied by are 1 over J40 and plus 1 over 40. Now we'll move Vs over to this side of the equation. We can see that this is negative Vs over J40. So we'll add that to both sides and we'll get this is equal to Vs times 1 over J40. So now we will just divide both sides by this number, whatever it is. The easiest way to divide both sides by this number is to do it on your calculator. Type this in, make sure you use parentheses. So this will give us V7 is equal to Vs times 1 over J40, and we're also dividing by this whole number right here, so that number will be in here, 1 over J40 plus 1 over 40. And if you type that into a calculator, you get that V7 is equal to Vs times 1/2 minus J 1/2. So that's our relationship between V7 and our source voltage. So what we're looking for is, well, actually let's get an explicit value for V7 first. We know our source voltage is 80 times cosine of 5,000 T. This is oscillating at a constant frequency, so we can put it in phasor form. This is in phasor form, this is 80 volts with a phase shift of 0 degrees. So now we can substitute this in for Vs, and we get that our Thevenin voltage is equal to 80 phase 0 times 1/2 minus J 1/2. That is equal to 40 minus J40 volts. Now, what we want is the RMS value of this. There's a formula that says that the RMS value of any sine wave, let's say VRMS, is equal to the magnitude of your voltage, which in this case, okay, we'll go over that. Magnitude of your voltage over the root of 2, square root of 2. So that's for sinusoid. It has to do with the shape of the wave, but that's not part of this problem so much. So we have to get the magnitude of this voltage. Now I know that for a complex number in the complex plane, actually 40 minus J40 is going to look like this. This is our imaginary axis, real axis. We'll have 40 on the real axis, and we'll have minus 40 on the J axis. And when you bring those two down, that's your point right there. So we want to find the magnitude of this line right here. That's going to be our magnitude. And we know from trigonometry that when you have, we try and find the hypotenuse, right? So our magnitude of our Thevenin voltage is going to equal the square root of our real part squared plus our imaginary part squared. But since we're just looking for the magnitude, it doesn't matter that this part is imaginary. We're just looking for the length of this line. So this is, again, just 40 squared. And this is equal to 40 times the root of 2. Is that right? Yeah. because this is actually inside here, we have 2 times 40 squared. You can factor out the square root of 2, and then you have the square root of 2 times the square root of 40 squared, which is just 40. So that's our answer. And now for our RMS value, we'll get V7 and RMS. We know from this little formula that it's equal to the magnitude divided by square root of 2. So if we divide this by the square root of 2, 40 times the root of 2 divided by the root of 2 is equal to 40. So that is our RMS value of our Thevenin voltage. Okay, now that we have a value for our RMS, or our V Thevenin RMS, this is the magnitude of that. We can plug that into our equation for power. We're looking for this. This was what our problem asked us for. So now we can plug this value in right here. So we will get maximum power is equal to 1/4 times this number, and it's squared in this equation. We've got V squared. We'll have 40 squared over RL, which again is the real part of our load impedance. We solved for our load impedance in our first part of the problem, and we got that our load impedance is equal to 20 times 1 plus J. So we want the real part of that. If you distribute this 20 over this complex number, you'll get 20 plus J20, and the real part of that is 20. So this is over 20 ohms. Now this is equal to 40 squared is equal to 1600, and 4 times 20 is 80. Our answer is going to be in watts because we're working with volts and ohms. So 1600 over 80 is equal to 20 watts. Now that's our maximum power that's transferred to our load, and we already found the load impedance to be our optimal value where we get maximum power transferred. So with this source voltage, this is absolutely the most average power that this circuit can deliver to any load. So that's our problem.